Welcome to Pentair Training Institute webinars. Today we're going to be talking about sizing submersible pumps and, more importantly, advanced curves, focusing again on submersible pumps. Now, one of the things I'll tell you is that we do take feedback from students, and I highly encourage you always to leave us a little feedback. At the end of this presentation, we do have a little card that says, again, you get to build these, so let us know. One of the feedbacks we got is that we want more on NPSH, and NPSHR, and NPSHA. So that will be a separate webinar. We're planning possibly in one webinar for November or December. So do keep a heads up for that. So today we'll be talking about the advanced curves, focusing on submersibles. Before we always start, I like to do some introductions about other learning opportunities. Remember, we always have the Pentair Learning Center, or the PLC, which is out there on the web, hosted by LearnUpon. It has interactive e-learning modules, product updates, live and pre-recorded webinar schedules and postings. So there's a lot of good information. The best part of this information is that it's free. If you'd like to sign up or to find out about any training opportunity, always go to our websites under the resource tab. Under the resource tab, you'll see learning opportunities. So one of them, which is of course highlighted, is the Pentair Learning Center. You can follow us too on facebook.com/Pentair Training Institute as well. The Pentair Pro Dealer Program, any company, your gas company, where you purchase your gasoline, your shopping centers, all these have some sort of rewards program. So of course we do. So take advantage of it. More importantly, if you're an installer or a driller, look into it, because we do have labor and extended warranty programs in there. So it's really worth looking at. www.pentairprodealer.com. For dealers and distributors, of course, we have the Pentair Access Portal that gives you 24/7 access to product availability, pricing, order status, delivery, copies of your invoice, etc. It's a good little link. A lot of people like it. If you haven't signed up yet, give us a call at 866-880-3771. Miss Amy will be happy to work with you. Last but not least, of course, we have our Pentair Factory Schools. We have at least 2 here in Delavan each year. We often feature them in Grand Island, and starting in 2018, we are going to have another remote location. We're looking to do one on the East Coast. So stay tuned for us. Follow us on Facebook for updates. We do the water systems and the ag schools. Even when we do the traveling schools, we try to incorporate lab time and work time. One of my goals is not to have you sit more than 90 minutes, because I'm an adult too, and I don't like to be lectured for more than 90 minutes or so. So we try to keep you moving, keep it interactive, and really focus on what your needs are. If you would like to have a school in your area, always reach out to us, or more importantly, reach out to your salesperson for that territory. They're more than happy to work with you, and I'm more than happy to work with them and get this all organized for you. We're going to start talking again about the advanced curve today and focusing on submersible pumps. And when you're going through this, one is that we want you to understand there's a lot of good information out there, and more importantly, I incorporate into this the sizing programs. The sizing programs, if you're not using them, you can't break them. Start playing with them, because there's a lot of good information, and you'll see that here as we go through the program. Looking today here's your advanced curve. And your advanced curve is going to have some very basic information. The first curve you see is this is your gallon per minute in your head curve. This is what the pump can do. That triangle that's highlighted there to the right is the best efficiency point. Now this is a standard generic curve. It doesn't show the point of usage. So it's showing the BEP, best efficiency point. Now you'll also notice that this is a rather flat curve. So depending upon your mission and what you're trying to do, often just the shape of the curve will help you determine what pump you may or may not need to use. The next thing there, like I want to highlight, is your BEP, your best efficiency point. Now, a lot of people will tell me that the best efficiency point is always the center of the curve. And if the manufacturer designates that to be true, you are correct. But I always look at the best efficiency point mark. Now, notice that this pump runs out at 140 gallons per minute. It can flow as little as about 33 gallons per minute. I say as little as 33 gallons per minute because that is that line designating the minimal, constant, sustainable flow. You really don't want to operate below that, especially with a variable frequency drive. Too often people think that the variable frequency drives or the variable speed drives that they're some sort of magical miracle silver bullet cure for everything, if you will. And I don't believe that to be true. You got to use your common sense. A pump can't do 120 gallons per minute and then turn around and do 10 gallons per minute. It's just not going to happen. So we have our best efficiency point, and you'll notice in this case it's about 120 gallons per minute, which is actually to the left of center. So again, don't assume that the center of the curve is always your best efficiency point. You have your power consumption curve. That's the top curve there. That's now highlighted in red. That, if you notice, this is a 25 horsepower motor, but you'll notice it exceeds 25 horsepower. Remember, all motors have a service factor. It's typically safe to assume that when you're talking submersibles, you're talking about a 1.15 service factor. And what service factor is you take service factor times the nameplate horsepower, and that will give you the true horsepower rated for the motor. So a 25 horsepower motor, which is a 1.15 service factor, can actually operate well over 28 horsepower. So we're not overly concerned. Now, the other thing people will say, well, that's very unique to your company, isn't it, that you always run to the service factor? And the answer to that is no. All companies do it. They're all often in the service factor. Now, we'll talk about that a little bit later too. If you don't want a non-overloading motor, there are options. But we'll discuss that here in later slides. The green line you now see, that's your efficiency curve. And I'll tell you, if you look at the best efficiency point, you can see that obviously the efficiency curve is skewed to the right. That's why I caution people, don't assume it's always going to be dead center to the curve. That's your minimal, constant, sustainable flow. That means if you're operating less than that, you're going to have issues with the pump. It could be upthrust, cavitation, other issues. So do be cautious. The last line is net positive suction head required. And a lot of people get confused with that. What does that mean? Is it submergence? Is it this? Is it that? Well, let's break it down and let's look at it. Okay, so what is net positive suction head required? Well, simply it is the amount of feet of water needed to keep the water that's entering the eye of the impeller in a liquid state, which means absolutely nothing to most people. And I'll be blunt. I forced myself to fully understand net positive suction head. I took the time and said, listen, as an educator, I must understand this. So I took the time and broke it down. To the right here, you see a lot of information, including water temperature, vapor pressure of the water at that temperature, the true atmospheric pressure. All this comes into factor. Let's break this down to you a lot easier. Okay, first of all, if I have a pipe that's 35 feet long and I'm at sea level and I put a vacuum, a perfect vacuum, on top of that pipe, I would draw water up 33.9 feet. That's because I have 14.7 pounds of air pressure pushing down on the water at sea level. 14.7 times 2.31 is 33.9. Now, one of the things I would tell you, be it submersible that we're speaking of, be it centrifugal, no one builds a perfect pump. If anybody ever told me they built a perfect pump, I'll tell you that person's a liar. And I'm not being mean, it's just a fact. We're human beings. Your pencil has an eraser because you make mistakes, so does mine. That means that when we build these pumps, there's imperfections. The parts have to have gapping in order for them to spin freely with the water lubricating them. Okay? You have machine errors. Machining might not be perfect. Assembly errors. You might not set these properly. You have wear and tear. So no pump will draw from 33.9 feet. Now, I'm a conservative guy. I say where that magic number is 25 feet. 25 feet of head is given to us by the atmosphere. Okay? And why I pick 25 is because I'm a little conservative. I've heard some people teach 27. And that's fine. Whatever number you're comfortable with, that's fine. But I'm going to pick a practical number of 25 feet of head, basically assuming that's what the atmospheric pressure will give me. Now, what is net positive suction head required? Because the water is going into the pump at a greater velocity than it would free flow, it's going in at a higher velocity, creating a low pressure point at the eye of the impeller. Net positive suction head is telling you how much feet of head you need over that impeller to keep the liquid liquid. In our previous example, we have a pump that has, let's say, 28 feet of net positive suction head required. So I know I have 25 feet of atmospheric pressure. I subtract from that 28 feet that the pump requires, and I have a deficit of 3 feet. That means in order to keep the liquid in liquid state, I must submerge the pump a minimum of 3 feet to satisfy the net positive suction head required. Do not confuse this, because I know you're saying, well, what about the submergence? Submergence will cover it. Don't confuse it with that, because I want you to understand we're trying to just satisfy one condition, okay, net positive suction head required. Another example, if we looked at the data sheet earlier shown, that net positive suction head required, we were estimating, if you look at it, that line, we would guess it was about 20 feet. I actually looked up the data on the pump and found that the net positive suction head required at that 119 gallons per minute was 18.38. So what does that tell us? That tells me I take 25 minus 18.38, and I have 6.62 feet of positive pressure, so to speak. That the pump is not really worried about submergence too much. Not to say you don't submerge it, you always submerge the submersible pump. But we've met the need just with the atmospheric pressure. Now, the customer throws a curve at me and he says, well, wait a minute. This is going to be at an elevation of about 4,000 feet. Now, if you had any of our classes earlier, you'll know that for every 2,000 feet of elevation, you subtract 1 psi or 2.31 feet of head. So that means I'm going to lose for that 4,000 feet an additional 4.62 feet of head. So now if I have my first calculation of 6.62, I subtract that additional 4.62, that means I have 2 feet of still atmospheric pressure to play with. So I'm not too concerned. So I know, at least for the water condition, I will not cavitate the pump. Another way to look at it is if you take the 25 minus your altitude loss, which is 4.62, minus the 18.38 feet that the pump requires, you still see we have that quote positive 2 feet. So again, we're not worried. I would then look at submergence. You always have to make sure the pump is properly placed underwater. There's 2 conditions to satisfy. I want to make sure you understand that. Net positive suction head required and submergence. Now, people will say submergence, where do I find that number? You know, where is that? And I'm going to tell you, we're guilty of it. We unfortunately do not always publish it, but you want to refer back to the factory. And in the factory, if they don't publish it or they can't get you that number, my best key, and I tell customers, is always assume 10 feet. What we're trying to avoid with submergence is, as you see that diagram showing a standard drain has a whirlpooling effect. Well, so does a pump, because we're pumping water at a higher velocity than it would free flow. So in doing that, we can create vortices or vortexing that will pull air into the pump and possibly airlock it. This is airlock, not cavitation damage. They're very, very different in what they'll do to the pump. Okay? When in doubt, assume 10 feet for submergence. So in our earlier case where we had a positive 2 feet of atmospheric pressure still to play with, I would still submerge that pump 10 feet to be safe. The key is you need to satisfy both conditions. Now, let's look at this curve a little bit more in detail. We're going to look at here and see that with the best efficiency point, that gallon per minute, I'm going to call it roughly about 119 gallons per minute. Now, the pump is rated as a 120 gallon per minute nominal. 119, if you ask me, is pretty close, so I'm not going to argue with the manufacturer on that. At the total dynamic head, boy, I'd be guessing, and I would say, well, I think that the total dynamic head might be about 720 maybe. I don't know. But I can guess. Now, the power curve, we're looking at that, and I call that about maybe 28. Okay, and that's that red line. And I look at my gallon per minute usage, and then draw a line, follow it over to my horsepower rated, and I'll see about 28. My best efficiency point, be looking at that, and I'll be guessing about 75% efficient. Finally, my net positive suction head, which I already told you was 18 point something, but if I looked at this curve, Would I get 18.38? No. I would guess. I'd call it 20. Now, curves are great. They give you a good ballpark. When I'm looking and sizing pumps myself, I always look at the curves first because obviously this is a nice depiction. I can see if I'm even in the ballpark. Then I can drill into, especially when I'm using a sizing program. And I want you to understand all pump companies have sizing programs. We're not unique in that. And often they're very similar programs. So once you get to know how to use one, often the competitors are very similar. But all of them are going to give you some sort of pump performance data sheet, which will give you very specific information. Okay, it will tell you the model number of the pump, the stages and such, as you see on the right upper corner there. But more importantly, it'll give you precise data of flow. At best efficiency point, it's 119.3 gallons per minute. It's 704.2 feet ahead. And remember, I guessed 720. Boy, was I off. So that's where we want to look at the data sheet. Now, at the efficiency point, I said about 75. Let's say 74.35. That's pretty accurate. It was a pretty good guess around that. The reality is, it's a memory game for me. As I'm sure you know, probably give this lecture multiple times. So I always can't remember every number. There's our 18.38 of our net positive suction head required. That's where I got that number in that earlier example that we did the math with. So here you find your exact number. You'll also see the power rated at the best efficiency point is 28.53. Now the power at the maximum rated diameter is 28.74. And I know customers would ask me, and they'll say, can you trim that impeller and a submersible? And the first reaction is no. But remember, we're talking larger pumps here. We're talking 6, 8, and 10 inch, maybe even 12 inch or larger bowls. You may not necessarily trim the impeller, but often what manufacturers will do will have an A, B, C type of system where impeller A has this diameter, impeller B has this secondary diameter, and impeller C has a tertiary, a different diameter. And each one will have a set head that they can produce. And by using a sizing program, it might tell you to use, say out of that 16 stages that we are using at this pump, it might tell you in order to reach your data point to use 14 of a C, 1B, and 1A to get the total dynamic head you need. So often, especially if you build your own submersibles, if you're in the build program that we offer through Berkeley, you will be doing this sometimes. So always remember the smaller diameter impellers are always on top. Now, we have our data sheet. We have very good numbers that we got from that pump. One thing I want to emphasize, when you're talking about a synchronous speed motor running one fixed RPM, you'll have a hard data output. Now, this is a much lower flowing gallon per minute, but if you see here, this pump builds a maximum of 148 feet ahead, and its run out is roughly 29.5 gallons per minute. If I were to ask you at 15 gallons per minute, will this pump hit 150 feet of head? And most customers, of course, will say, no, you're to the right of the curve, you're above the curve, you're more than what the curve can do. Many expressions to explain it. But the simple answer is that duty point of 150 at 15 gallons per minute is not obtainable. In fact, I don't even think this pump could build 150 feet of head. As we say earlier, it looked like it did about 148. Now, what it will do is at 15 gallons per minute, where it intersects the curve, is 120 feet of head. That's what it will do. So it will do no more, or it will do no less. I want you to understand, if you say put a dole valve in there or some sort of flow restrictor to allow it to flow only 15 gallons per minute, it will then do 120 feet ahead. Okay? Very precise. Now, here's a trick question, and I'm going to emphasize it's a trick question, so the answer better be no. Can this pump do 10 gallons per minute at 100 feet ahead? 10 gallons per minute at 100 feet ahead? And the answer is no. Your first instinct will be, but that's to the left of the curve, it's under the curve, it's within the curve. And those are easier answers to say than what is the correct answer. The correct answer is no, it won't do it. Understand, the pump can only do what the pump curve will allow it to do. So if I put a flow restrictor in there to only allow the pump to run 10 gallons per minute, if we extend the 10 gallon per minute line up to where it crosses the curve, it's roughly 132 feet of head. So you have to ask yourself, if that system requires 100 feet of head, and at 10 gallons per minute the pump's going to build 132 feet of head, what will that extra 32 feet of head mean in my system? For example, in an irrigation system, that extra pressure might mean the heads might miss. Might mean that you get overlap of arc, or you're watering the neighbor's lawn for free, for example. So you have to ask yourself, what will it do? Will it in fact maybe possibly damage one of the irrigation heads? Okay, so we have to ask that question. Now, let's say we put a pressure reducer valve in there. So now we're only going to let it do 100 feet ahead. If I extend it 100 feet ahead horizontally until it crosses the line, at the curve it crosses at roughly 20.5 gallons per minute. So if I restrict the pressure, that pump will want to do 20.5 gallons per minute. And if you're not pumping into a pressure tank or some sort of control device, say a cycle stop valve or such, that extra gallon per minute's got to go somewhere. Now, irrigation people, that just means you add extra heads, or maybe you run 2 zones together. But you have to know how to manage it, and you want to keep the pump running in its proper curve. If you said, but Dan, you talked about curving or trimming the impeller, or changing out the impellers. And the answer is yes, you can do that. But understand, once you do that, when you trim an impeller, when you change the impeller stack, for the A and the B and the C, understand you change the whole curve. That means, let's say this customer who wanted 10 gallons per minute, 100 feet of head today, decides to add a second zone that needs another 10 gallons per minute, 100 feet ahead, and they want to run both zones simultaneously. Once you trim an impeller, you forever cut that impeller. It's done. Now, granted, in this case, if we could pull the pump and take the B and A out, maybe put in different C's or whatever to change that head, yes, you can do so, but that's labor intensive also. That's why a lot of people are opting for variable frequency drives and using the original curve, but changing the RPM of the motor to meet the need. Now, what do we need to size a pump? Now, we've been talking about this with the curves. They're all based upon what? Gallon per minute and total dynamic head. Any pump you're looking at, those are your key features. What are your gallon per minute requirement and what is your total dynamic head? To understand that, I always like to start off with first, let's see what the system needs. Now, if you did my seminar earlier last month, we covered submersibles with a basic curve. And there too, we started with how do you size it. Now, for residential application, you do the fixture count method. You can look at the flow per fixture. However you choose to do it, that's fine. But understand, these charts are easily found. These were all found in my handouts, for example, that I give out for any class here in Delavan, for example, or in Grand Island. We have these engineer books. And these engineer books, we even have stuff like, for example, each person per day, for all purposes, budget 50 gallons per minute. Well, what a horse or a dry cow would drink. So even for agricultural purposes, we can tell you total consumption estimates. Now, if you don't like our numbers, trust me, there's that thing called Google out there on the interweb or the internet. You can get out there and you can find all these different numbers. Okay, you can Google it and you can find out maybe numbers from the Cattle Association, which you are much more comfortable with trusting their numbers. They might be different than mine. Okay, but my point is that this data is out there and it's retrievable. You can even look, for example, you say, aha, Dan, I'm an engineer. I need very precise numbers. Once again, from my engineering book, here's hospitals rated for 25 or less fixtures, figure gallon per minute per fixture. Now, this is just one engineering graph I found that we publish. There are plenty others. So don't say the data can't be found. My point is simply this. My first starting point is to find out how much water you need. Be it an agricultural project, be it an apartment, being a office building, be it a school, we can figure out your usage. Once we have the gallon per minute, the next question is, can the well or the water supply it? if you're limited to a city main, and that city main is 3 inches, and they're only going to give you roughly about 100 gallons per minute, doesn't matter what your fixture count is at that point. Your limiter is 100 gallons per minute. But now if you look at a well, and this is a review, well construction, I'll do this quickly because there's a few things I want you to remember. Okay, we drill down our well to hit the standing water level. We put our casing in, we put our well screen in, we put our pump in, and we start to pump and we create a cone of depression. Now I want you to understand every water source has a cone of depression, including an open body of water. Remember the discussion about net positive suction head and vortexing? Water doesn't replenish itself instantly magically. So you get this cone of depression. And as we start to pump the pump, we'll reach a gallon per minute and a equilibrium point where the water in the well drops to a point that's sustainable. Let's say it's 30 gallons per minute and it draws down 10 feet. So we know we're happy with that. We're getting 30 gallons per minute. We get 10 gallons of drawdown. It's steady. That equilibrium point or drawdown may also be known as the working level, the pumping level. Your local vocabulary may be very different than mine, but I want to make sure we all understand what we're talking about. Some people and some well reports, for example, in Nebraska, they don't care as much about standing water level. They just report often pumping level. That's been explained to me as I've been doing classes out there now. So depending upon your local codes and such and how it's reported similarly. When water is not plentiful, okay, meaning that the well cannot meet the demand of the system, and that happens plenty of times. My first option is to use a safety, some sort of electronic safety, be it Warwick sensors maybe, or some sort of water sensing system, be it a pump saver or RSPP system, or a variable frequency drive that has a lot of built-in protection to them. But also keep in mind you might need to use a dole valve to restrict the flow of water just to begin with. Maybe if that well is only producing 3 gallons per minute, that's the best you can get. Maybe put a dole valve in there restricting that flow to 3 gallons per minute to try to limit the taxation of the system. Safeties are one way to do it. A dole valve and multiple storage tanks is another way. Again, knowing we get 3 gallons per minute in a residential application, the homeowner might have 3 120-gallon tanks that at 30-50 give them roughly 35 gallons of drawdown. That means that homeowner knows he has 105 gallons of storage at 50 psi. So in the morning, they might take 2 showers and have to wait for the third until the evening. The homeowner can try to budget it. Just explain to the company you're working with what the limitations are and why the recommendation for tanks. Now again, a low flow, they might do it in conjunction to storage tanks and a booster pump. Just pump it into an open cistern or an open water tank and then draw out of that tank with a jet pump or a booster pump of some sort. In some circumstances, out east, I've heard stories where the water is only about a half a gallon per minute of production. So they'll drill the wells very deep and wide and use the well casing itself as storage. There, believe me, they want to know static water level versus drawdown level. Because static water level might push that water up to within, say, 50 feet to the surface. But that well might be punched 600 feet. And it might drop possibly during maximum usage of the home. It could drop easily 300-400 feet. So that pump has to be sized accordingly. Now, we satisfied our gallon per minute in the system. We're going to assume this, okay? That we know that the water table is going to produce what the home or the irrigation or the business requires. So let's assume that. We know our demand. We know the well satisfied it. What is total dynamic head? And total is everything. Everything. I'm assuming, I want you to make sure you understand, and I really drove this point home with the earlier webinar that was on submersibles, is that when you tell me total, that means you took into account the total dynamic head, including friction loss, all the way down to where the pump was set. If that pump was set down 1,000 feet, I assume, and I hate to do that, but when I hear total dynamic head, that you did the friction loss for that 1,000 feet of drop pipe. The service pressure, I again hopefully assume that you converted it into feet of head. And don't laugh at that. I've had customers take 50 psi and add it to the total dynamic head. And understand this, when you do that, you're cheating yourself by a factor of 2.31. Remember, 1 psi equals 2.31 feet of head. So be careful about that. Irrigation people, when you're looking at your friction loss charts, read it. Read that factory manual. Okay? Read all of it. If that little chart you're looking at, you got to make sure, is it reporting in feet of head loss or pressure loss? Okay? So watch that. Look at your elevation, especially in irrigation issues. If for example, in this later example I'm showing you, we'll have 0 feet of elevation, and I do that in the example because I want to make it simple and clean and quick for this webinar. But we have 2 branches in that system. One that goes to the left, one that goes to the right, or as you would see it, there's one that goes to the top, that one goes to the bottom of the screen. If the one that goes to the bottom of the screen is at 0 feet of elevation, and the one that goes to the top of the screen actually goes down 60 feet, that its farthest head would be 60 feet below rise. Do I worry about that? No. Because when it goes down, I'm not worried about additional elevation, I'm losing elevation. The installer would worry about it because he might need to put in a pressure reducer so he doesn't damage the head. But I don't worry about it as a pump professional. Conversely, if that was, say, 100 feet of elevation, where it's rising 100 feet, now my worst case, and here's the key word, words, I should say, is what is my worst case scenario? If I have one that's at 0 feet of elevation, but then the one on the top rises 100 feet of elevation, I must add that 100 feet of elevation in there. And then the one at 0 elevation, again, is not my concern. The installer might need to put in a pressure reducer valve, but he's the professional to do that. I don't worry about that. On that note, can you have rise in elevation going into a home? Absolutely. First of all, as a pump installer, where does my job end? It ends right at the tank. Now, if I'm a plumber and the pump installer, then I worry about that shower head on the second floor. But as a pump professional, our job ends wherever in an irrigation system the irrigation professional tells us. If he says the farthest head, or if he says the solenoid valve head right here at the discharge of the pump, wherever he tells us where to end that job is where we end the job. In a home, once you hit the pressure tank, we're done. With commercial projects, work with your specifying engineer or your professional engineer on the project. So getting back to total dynamic head, friction loss, surface pressure, elevation. Now here, standing water level, but more importantly, the drawdown or the working level or the pumping level. When I turn on my pump, how far is that water table going to drop? That is the key I need to know. I want to know the worst case scenario down in the well or the water supply. If it's an open bodied tank, like a cistern, if they're going to let that tank drop 7 feet each time before they refill it, I plan on that 7 feet of drop being my worst case scenario. Now, let's look at a practical example. We had a customer, and we're all discussing this now over coffee. Okay, so we haven't put anything hard in the ground yet. And the initial plan, the gentleman that we're discussing this with, is going to put 160 feet of 2.5-inch steel pipe down to the pump. 400 feet of 2.5-inch PVC pipe that tees into 2 150-foot sections of 2-inch PVC pipe. Then at the end of that pipe, he has this magical connection that was split it 7 ways, so that at the end of that 150 feet of 2-inch, there's going to be 30 feet going 7 ways of 3/4-inch PVC laterals that will go 5 gallons per minute and need 40 psi. And the first question I would ask real quick is, where is our point of usage? In this case, that tells me at the end of those heads, he needs 40 psi. So we have to calculate all the friction loss plus the end sprinkler pressure requirement of 40 psi. Now, like I say, we're talking about this over the counter, having coffee. He tells me that my well size that I work with is 10-inch. Does that really matter to me? Well, it just tells me I can put up to easily an 8-inch pump down in the well if I had to. But I don't think we need to go that big of a pump. Standing water level, he tells me it's 70 feet. And the drawdown, when I ask him, he says it's 60 feet. I asked him, what's the gallon per minute production on that well? He says, it's well over 120 gallons per minute. Here's a point of discussion. Once we determine our gallon per minute requirement, do we do any magical math to play with the number to figure out where the drawdown might be at that point? Meaning that I can do 120 gallons per minute and draw down 60. If this system only requires, say, 70 gallons per minute, do I take a percentage of that and assume, and there's that magic word, assume the drawdown will be less? My answer is no. Always take the worst case scenario. If you give them a little extra pressure, I'll tell you, very few people will argue with you that you gave them a little extra pressure. But in irrigation zones, see, extra pressure, they can adjust that with sprinkler heads, or they can even put in a pressure reducer valve. But let me tell you something, if they're short pressure, they're going to have you for lunch. They're going to be angry, okay, because their zones aren't meeting properly. So always round your numbers up when you're calculating, and always assume worst case scenarios. Well depth is going to be 175 feet. Now, for my educational purposes, if you ever take any of my webinars or classes, it's a generic rule of thumb, so we all get the same answer. We always set that pump 15 feet off the bottom. That is not an industry standard. That is an educational standard just for our purposes. Okay, so we're going to set that pump at 160 because of that 15-foot rule. Elevation is 0. I'm being nice to you. We're not concerned that the top branch is 70 feet higher, 100 feet higher, 60 feet lower. Whatever I said before, they're both equally spaced and equally level. System pressure desired, we found that out. Remember, 40 psi where? At the end of the sprinkler head. Power supply is 460 volt 3-phase. Well, okay, that's great, because especially for an irrigation project, I like to see 3-phase. 3-phase draws less amps, so it's easier to work with as far as for the customer for what they pay for over time. If you took my webinar or you're watching this advanced curve webinar, I assume you, of course, have been in the business. Now, shame on me if you would like to have seen the friction loss charts, but I'm not showing them here just for time's sake. So that being said, Dan, be quiet and keep going. Well, let's look at the friction losses. System required 70 gallons per minute. How do I know that? Well, he has 7 branches off of 2 zones. Okay, we have 7 30-foot 3/4-inch pieces of pipe that go to each sprinkler head. So 14, and they each need 5 gallons per minute. That gave me 70 gallons per minute. Looking at 2.5-inch steel pipe, I have 160 feet of drop pipe. Divide that by 100. Why am I dividing by 100? Because that's what the chart I'm looking at is based upon, 100-foot lengths. And I get 1.6. I take the friction loss per that 100 per the chart I saw, and it came out to be 6.64. Multiplying the 2, I came up to 11 feet of loss, rounded up. The 2.5-inch plastic, that's going 400 feet. 400 divided by 100, again, because the chart's based upon 100 feet, gave me 4 pieces. I take that, multiply by the friction loss I found per 100, at 70 gallons per minute, okay, it was 3.58 feet per 100 foot. Multiplying and rounding up, that came up to be 15 feet ahead. Now, here's my next question. I went up 160 feet. I went 400 feet. What am I doing in the 2-inch pipe? Think about that for a minute. First of all, I'm going 2 different directions. That's correct. Second of all, I'm going equal distance. So if I'm looking at my worst case scenario and I know the elevation is the same, if I can go 150 feet to the down position, the solid line, can I go 150 feet of push to the dotted line above? Okay, if I can get water to the bottom 150 feet, of course I'll get it to the top. So my worst case scenario is 150 feet. But here's the key to remember. What happens at that T? The T splits the pipe and it splits the flow. So it sends the flow 2 directions. 35 gallons to the top, 35 gallons to the bottom in our illustration here. Okay? Because each side is going to be regulated by the sprinkler heads. And the combined sprinkler heads each flow combined flow 35 gallons per minute or 5 gallons per minute each, okay? So we have equal flow left and right. That means, see, if I can get to that side, I will get to that side. In my calculation, the 2-inch plastic, I know that I have 150 feet divided by 100 is 1.5. I'm going to multiply it by, again, that friction loss per 100 feet, which is at 35 gallons per minute now. Gives me a number of 2.36 feet of head per 100. Do my math and I round it up to 4. Same thing with the 3/4 inch now. If I can get to that 3/4 inch 30-foot section, can I not get to that 3/4 inch 30-foot section? They're all equal distance. Also, remember the limiter is the sprinkler head. I'm only flowing 5 gallons per minute down each one now. Singularly, each one. Okay, so I have 30 feet divided by 100, because again, the chart's based on 100 foot, is 0.3. Per 100 feet, my friction loss in 5 gallons per minute is 5.66, which seems pretty high, but remember, we're only going 0.3 feet, so my total is 2 feet of friction loss. All right, so let's figure out our total discharge head, our total dynamic head. Pumping level is 130 feet. Now, where'd I get that number? 70 plus 60. Always place yourself to cover the worst case scenario. If you hear at 120 feet, that's going to drop to 60 feet down, I'd still calculate it as 130 feet, taking into consideration that full 60 feet of drop. Service pressure in feet of head is 93 rounded up. Friction loss in that 2.5 inch steel is 11. In the plastic, it was 15. And the friction loss in the 2 inch was 4. And the 3/4 inch came into 2 for a total of 255. Okay. So let's now go to a sizing program. Now, this one in particular is our Stay Right site. And you'll click on the sizing program there. And it's going to ask you to, quote, launch it or load it. You're not putting anything on your computer. Don't worry, because this is a huge database. We don't have a mobile version for that reason, too, because it's a huge database and we don't want to upset our customers by taking up all your memory. But can you link to this with a mobile device? Absolutely. So let's get into the program, and we're going to do it by conditions of service. Now, if you want to do it by product line and then pull up the generic curve for the product for a specific product number or pump ID, for example, you want to look at the JHC, the little little centrifugal high head half horse, you could do so. But I'm gonna search versus the conditions of service, and when I do that, you'll see this right here, the top. You'll have 2 blanks under U.S. gallon per minute and feet of head. Okay, right there. I'm going to put in my 70 gallons per minute at my 255 feet of head and hit the next button, which would then bring up the product line. Now, we know we're talking a submersible, so we're going to look at the 4-inch submersibles. And when I click the next button again, I'll get these thumbnail sketches. And you'll notice the first one has a little warning triangle saying it's a near miss. Let's click on that and find out why. Well, if you look right here on the data sheet, you'll see in the red, I'm asking for 255, and it's not going to hit that. It's only going to hit about 248. And that gives me a fair question to ask. Now, again, I'm saying this is a conversation over the counter. And we have this conversation, and I said, hey, is that close enough? Okay, is that going to be, you want 255, I'm going to get you 248. Even looking at the curve, you see how it's a whisker off. And what my irrigation professional would probably tell me is, Dan, you know I can't have less pressure. I can always deal with more, but I can't deal with less. Fair enough. That's fair enough. So let's take a look at it. Now, I want to tell you, we're only talking about this. Nothing has been put in the pipe, or no pipe has been put in the ground. We haven't committed. Looking at this, I know my 3/4 inch and my 2 inch is going to be minimal savings. Where can I save the most? And looking at our math again, we look at the 2.5 inch steel and the 2.5 inch plastic. That was 26 feet of head. Now, looking at the cost comparative, some guys would tell me yes, some guys would tell me no. Often 2.5 inch is hard to find, so it's more expensive. So let's look at 3 inch. How far do I have to run that 3 inch and how many gallons per minute? It's still 70 gallons per minute. And it's still, for the 3 inch steel drop pipe, it's still going 160 feet. So that's 160 divided by 100 is 1.6. But looking at my 3 inch chart, I found that the friction loss per 100 is 2.5. Doing the math, I rounded it up to 4. You see right there alone, I've lost, 7 feet of head. Which that alone might put us where we're happy. But let's look at the 4-inch plastic. The 4-inch divided by 100 will give us 4 because our chart is based upon 100 feet. Now, the friction loss per 100 was 1.15 multiplied by 4 gave me 5 rounded up. Just by having a conversation over coffee, we went from that 26 to 9. We figured out our friction loss issue. We found again, now let's do the math. Our total discharge head, it's still 130. My service pressure didn't change. I still need 40 psi, so 40 times 2.31 is 93. Remember, always report in feet of head. Friction loss in the steel, 3-inch, was 4 feet of head. 3-inch in plastic for the friction loss came out to be 5 feet. The friction loss in the 2-inch plastic remained the same at 4, and that friction loss in the 3/4-inch plastic remained at 2. But this time, my total dynamic head was 238. Going back in there, I'm going to type in where I had the 255. I'll correct that to 238. And now look at my curve. Talking to the pump professional, my irrigation professional, I asked him, how do you feel about that? He says, a whole lot better. Whole lot better. Okay. Now, I also want you to point out, if you notice, this chart in gallon per minute goes 0 to 140. This is a 70 gallon per minute pump. Okay, that we are looking at. In this case, would I assume that 70 gallons per minute would be my best efficiency point? That's a correct assumption. Absolutely. Always try to find the best efficiency point where it's marked. If it's not, if it's a 10 gallon per minute pump, you assume 10 gallons per minute is its best efficiency point. In this case, we're running a 70 gallon per minute pump. I would assume 70 gallons per minute is always its best efficiency point. In this case, it happened to be dead center. Now, customer says, well, Dan, what about a variable frequency drive? What would that do for me? And what I wanted to show here is with that same curve we're working with, there's a tab in the sizing program marked multi-speed curves. With one push of the button, I can generate multiple speeds. Now you'll notice the bottom red one there, it's giving you a warning it's not possible or out of alignment, whatever you want to say. It's because there's this golden rule of variable frequency drives that we don't go below 1800 RPM. If you look at this one, you notice the RPM on that red line is 1700 and some. It violates that rule. So that's where we want you to notice that. And one quick way to fix that is go up to that last one where it says the 1700, make it 1801 for RPM and hit recalculate, and now that line will turn blue again. All right. We also can do multiple conditions. This customer says, Dan, during the season, he might not need the full 70 gallons per minute. We might ratchet it back and put different sprinkler heads in there. Say, for example, in the early spring, when there's plenty of water, we'll have less flow. So let's look at the multiple conditions. And you can click on that. And what you can do is I can then put in there 70, 65, 60, 55, 50 gallons per minute. I change the gallon per minute. Okay? I then hit recalculate, and it gives you multiple points. See how I kept the total dynamic head the same, but I changed the gallon per minute usage. Then I got really fancy and I went into the multi-speed curves. Now the multi-speed curves will not draw these out instantly. It'll have that same RPM set you saw before. What I did is I did the math, and it took me hours upon hours to do the math, and calculated exact RPM and then plugged it in. And if you believe that, knowing that I hate math, you know, I got a bridge to sell you to. No, I didn't. Of course I didn't. I played with the numbers. Remember, when you pull up a multi-speed curve, just how I told you to correct that one red line, I can go to each line and adjust the RPMs to get them to line up basically with each point of usage, to give the customer an idea of approximately how much RPM it would be. And more importantly, if you look at the power curve, the power HP curve, you'll notice that it gives you less power, of course, with less RPMs. So the customer can look at potential savings that way. Now, in a residential application, would I promise you a big savings? No. But remember, now we're talking irrigation and larger units here. Now, this is a 7.5 horsepower. But if you're running, say, a 200 horsepower system, Variable speed curves become very critical, where a lot of customers will see that the investment of a VFD drive will in effect pay for itself when you're using a larger system. But this is a nice way to give the customer a nice diagram. And that's the point of this multi-speed curve right here. If you can explain to the customer that with the investment of a variable frequency drive, you can flow as little as, say, 50 gallons per minute versus flowing to full 70 gallons per minute. And at 50 gallons per minute, you'll be running only about 5.5, maybe 5 3/4 horsepower. So you'll be saving amps in the motor, which saves heat in the motor, which extends the life of the motor, and it also consumes less watts. So it's one thing to explain it to the customer, but to be able to show the customer and then give them a piece of paper to let them think about it on their own is very imperative nowadays. It's not enough just to say you should do it because I said so. Okay, customers want to, it's funny where, remember when we were 3, or when your children were 3 and they always asked why? Everyone's doing that now. It's acceptable to keep asking why. Explain this to me. I want to understand it. This is one more tool to let you understand that. Now, the other thing I'll point out in this curve, if you notice, it doesn't have the best efficiency point or an efficiency curve. Because here we assume 70 gallons per minute is the best efficiency point. A lot of smaller pumps don't have efficiency points necessarily drawn out or a curve for the best efficiency, nor does it show net positive suction head required. Because typically when you're talking smaller pumps, the atmospheric pressure of 25 feet will satisfy that, so you worry about submergence. When you don't see a submergence listed, like in this curve, then always assume 25 feet. So there's your power consumption curve. I want to take the time here real quick to say thank you very much for spending this time with me. I greatly appreciate it. Again, understand that these webinars that you hear are always open to your suggestion. Like I said earlier, people were asking me, can you have more information on net positive suction head? So we plan on doing a webinar just on that. So you can impact these projects. You can have an input. Let me know what you think. Let me know what you'd like to see. Send us a note at training.institute@pentair.com, as you see on the board there. Again, thank you for your time. I hope this helped. And this is Dan coming to you from the Pentair Training Institute. Have a great day. Thank you.